A massive electric motor begins to turn. Outside air is pulled through several compressor stages, then forced into a storage volume deep underground. There is no lithium and no electrochemical reaction, only air, pressure, and a cavern large enough to participate in grid-scale energy storage. But the moment charging starts, a problem appears. The harder air is compressed, the hotter it becomes. If that heat is removed and discarded, the plant throws away an important part of the compression work. Later, when the air expands to generate electricity, it cools sharply and needs the very heat that was lost. So how can an advanced compressed air plant store both pressure and compression heat, then reunite them hours later to drive a generator without burning natural gas for reheating? Above ground, the plant resembles an industrial turbomachinery complex. Large pipes, compressors, heat exchangers, expansion turbines, motors, and a generator. Its largest component may be almost invisible. The air store can be an underground salt cavern or another pressure storage structure selected for the geology and system design. During charging, surplus grid electricity powers a motor connected to the compressor train. Instead of reaching final pressure in one step, the air normally passes through multiple stages. Each stage raises pressure and temperature. Heat exchangers between stages remove heat from the air before the next compression step. The compressed, cooled air moves into storage. The recovered heat moves into a separate thermal energy store. Depending on the design, that store may use a packed bed of rock or ceramic material, or a heat transfer medium connected to insulated tanks. The original electrical work has now been divided into two accounts. Compressed air holds pressure potential, while the thermal store preserves compression heat. When the grid needs electricity, a valve releases the air. Before entering the expander, the air receives heat from the thermal store. It then expands through one or more turbine stages and turns a generator. The loop appears simple, but if either store fails to perform, much of the advantage disappears. The first enemy is thermodynamics. A compressor performs work on a gas, increasing its internal energy and temperature. In conventional diabatic compressed air energy storage, compression heat is rejected. That protects equipment and reduces air volume before storage, but it also removes useful energy from the cycle. During discharge, the cold air must be heated before expansion. Existing diabatic plants may burn natural gas to supply that heat. The result is a compressed air battery that still consumes fuel while generating. It retains pressure, but not the complete energy history that created that pressure. The second enemy appears in reverse. Air cools as it expands from high pressure to low pressure. Without enough reheating, turbine output falls, water can condense or freeze, and equipment experiences severe thermal conditions. Too little heat leaves pressure energy underused. External combustion can restore temperature, but it changes the fuel use and emissions of the storage cycle. Heat also refuses to remain perfectly still. During hours of storage, it migrates through insulation, vessels, and piping. Air in the cavern exchanges heat with the surrounding rock, so pressure, temperature, and mass flow vary during operation. Pressure drop through heat exchangers, leakage, electrical losses, and mechanical friction remove additional energy. Building a larger cavern does not make those losses disappear. The real engineering question is how to arrange two different energy stores so that heat returns at the correct temperature, time, and direction of flow. The core of advanced adiabatic compressed air energy storage, or AA-CAES, is the coordinated compressor, heat exchanger, and thermal storage train. The goal is not to hold the entire plant at one temperature. It is to control heat flow and reduce the large temperature differences that create irreversible losses. During charging, several compressor stages divide a large pressure ratio into smaller steps. After each step, a heat exchanger extracts energy from the hot air. Intercooling can also reduce the work required by the next stage because cooler air is denser and occupies less volume. The recovered energy enters the thermal store. Imagine a vessel filled with solid material and countless flow passages. A hot fluid moves through the bed, transfers heat to its surfaces, and creates a thermal front that advances through the material. A well-designed store prevents the hot and cold regions from mixing too quickly. During discharge, compressed air or an intermediate heat transfer fluid passes through the system in the recovery direction and returns heat to the air before expansion. Meanwhile, the cavern performs a different job. It provides volume for a large mass of high-pressure air. Storage duration can therefore grow by increasing usable storage volume, while charging and generating power depend mainly on the ratings of the compressors, heat exchangers, expanders, motor, and generator. This partial separation between energy capacity and power equipment is one reason compressed air energy storage is considered for long-duration storage. During discharge, cavern air is not simply allowed to rush into the turbine. It first passes through the reheating chain, then expands in controlled stages. Reheating between stages may keep temperature within equipment limits and improve useful work recovery. The turbine shaft drives the generator and converts recovered mechanical work back into electricity. The word adiabatic does not mean that no heat transfer occurs anywhere in the plant. In this technology family, it describes the strategy of retaining and reusing compression heat inside the storage cycle instead of rejecting it and later replacing it with fuel combustion. Heat exchangers are therefore central, not optional. Final efficiency is determined by the complete chain. If a compressor and an expander each operate at 80% efficiency, their simplified combined ceiling is already 64% before motor generator, pressure drop, leakage, and thermal storage losses are included. A 2023 assessment by the United States Department of Energy gives an upper bound of about 70% for adiabatic compressed air energy storage. That is a category-level bound, not a promise that every plant reaches 70%. The plant can now operate as a coordinated system with two energy streams. When wind or solar generation exceeds demand, the motor accelerates the compressor train. Compressed air travels toward the underground store. Heat extracted after the compression stages enters the thermal store. The two portions remain separate because they require different volumes, materials, and operating conditions. When grid demand rises, the energy flow reverses. Air leaves the cavern, but it receives the stored compression heat before expanding. The warmer air carries greater potential to perform useful expansion work. The turbine remains within its intended thermal range, and an advanced adiabatic configuration can avoid natural gas reheating. The opening loop is now closed. The plant does not place electricity directly inside the air. It divides compression work into pressure and heat, preserves each part with suitable equipment, and synchronizes them again at the turbine. This does not create a lossless machine. The geological store must remain stable and sufficiently tight. The thermal store must preserve a useful temperature profile. Heat exchangers must transfer large amounts of energy without excessive pressure drop. Compressors and expanders must operate efficiently while cavern pressure changes. Moisture must be controlled, and auxiliary equipment consumes power. The coordination of the entire chain, not cavern size alone, determines whether the plant performs well. Advanced adiabatic compressed air energy storage solves a basic paradox. Preserving the useful energy of compressed air requires more than preserving the air. The system must also preserve the heat created while compressing it. The air store provides energy capacity. The compressor and turbine train sets power. The thermal store reconnects the two halves of the cycle and allows electricity to be recovered without recreating discarded heat by burning fuel. That is how an underground cavern, a thermal storage mass, and a train of rotating machines can function together as grid-scale energy storage, not through chemistry, but through precise control of pressure, temperature, and time.